Now let us start potential barrier. As we have solved potential step, just like we will solve potential barrier. This is also application of Schrodinger equation in one dimension. For this, we will again look for potential, how it looks like. So, this is x, that is for one dimension, taking 0 and point A. At 0 we are taking Vx and V naught height we are considering for up to point A. Join here. So, this is V naught. I want to draw by showing red lines, actual potential shape. This is here. This one, making outline for clearance. So, this is what represented by red line showing potential barrier. Just we have read about potential step. In that we have this x and Vx at 0 and V naught height. That is, in that we have only two regions, left and right, in potential step, but in potential barrier we will have three regions, region first, second and third. So, this will be region first, this is region second, that is 0 to A, and this part is region third, that is again greater than A. So, defining potential using Vx of the form, its value is 0, this Vx is 0, this is V naught and this is 0, but when 0 for x less than 0, V naught for 0 at 0, greater to 0 at A, okay, but not greater than at A, this A, and for again 0, x greater than 0. So, this is three reason for potential. So, this is what showing potential barrier, whereas in potential step two regions, in potential barrier three regions. As we know that we take particle, beam of particle, and we study using quantum mechanical concept. So, now taking that one, here we have beam of particles, so we can show here these waves, y waves, because when particle moves, then there is the wave packet associated with that. Now, so drawing this waves, like this. Amplitudes variation is there. And something straight. Okay, what we want to show here, now this is of more importance. We considered beam of particles which incidence from left side towards positive axis, and that beam of particles can be treated as wave packets according to concept of de Broglie. Now, these particles will reflect or transmit. This is our main concern. So, we can draw here this outline. This is E. It means that we are treating with those particles whose energy is higher than this potential height. So, we have two cases for study. Case first, when energy of incidence particle, beam of particles, is greater than potential height, and second case is when energy of this beam particles will be less than this potential height. So, we will first consider case 1, and for that I have drawn here E. This represents that we are taking energy of particle is higher than potential height. Okay. So, we will see that classical view and quantum mechanical view. As well as quantum mechanical view. In both cases, so first we will deal case first. Okay. Now, in classical sense, when energy of particles, beam of particle is greater than these particle will enter from region first to region second, because higher of energy it will transmit here, and after region second to region third it will again transmit. It means that according to classical view there will be total transmission. According to classical view, total transmission. But when we will deal with quantum mechanical view, then we will see that it will not total transmit always, but it reflect also. That is, we will have quantum mechanical reflection coefficient as well as quantum mechanical transmission coefficient. This both value we will have. So, we will show by obtaining expression, and we will then differ again classical and quantum mechanical view. It is clear that we have drawn here half higher amplitude than of shorter than of shorter. Why it is? Because there is variation of amplitude due to change in momentum. If you will see here, momentum, what will be? Momentum is P is equal to under root 2 me. It means that we know P is equal to under root 2 me, general formula, or mean we can write, call that for kinetic energy. We may write one formula more. P is equal to under root 2m ek. This is our formula, that is kinetic energy. Kinetic energy is equal to half mv square, and we are representing this by ek. So when you will write m square v square by 2 by multiplying here m also, shifting 2 here, so 2m ek is equal to m square v square is p square, that is p is equal to under root 2m ek. So here is what? This is kinetic energy. Now consider for here in figure, here momentum, what will be momentum? Momentum will be under root 2m momentum in region first, so can be represented by P1, which will be 2m. Now what is total? If we see, total energy is equal to kinetic energy plus potential energy, that is kinetic energy is E minus V, total energy minus potential. So here potential is 0 for x less than 0, so this will be 2m E for region first. For region second, particles have momentum 2m E minus V naught, because in this region V is V naught. And for third region, again this is equal to this, because again 0, so we can write again P1. P1 is equal to 2m E. So when particle incidence from left side having amplitude, since kinetic energy is decreasing, so momentum is decreasing, therefore it will be slow down, therefore amplitude variation happens. And after again look, just here kinetic energy is less, here kinetic energy is more, so again particle will accelerate in third region. So therefore we have amplitude variation due to change in kinetic energy, or we can say due to change in momentum. Now we know that to study beam of particles in case of quantum mechanics, we use that particle as wave packets for when particle is in motion, and to study that motion we use wave function. So in this region we will take psi 1, here psi 2 and here psi 3. These are wave functions. In this region, when this waves incidence, then we can write plane wave equations for this. That is, first we write for the Schrodinger equation, then second order, and after we use solutions. So let us see now. We will show solutions, or we can say plane waves equations. So let us see. For region first, applying Schrodinger wave equation, since in one dimension, so del square psi 1 upon del x square plus 2m e minus v naught, but there will be only e, as we have discussed, minus v naught, that will be 0 upon h cut square psi 1 is equal to 0. This is, I am just recalling you, del square psi plus 2m upon h cut square e minus v psi is equal to 0. So for one dimension we write like this, and since in region first v is 0, so this will be 0, reaching equation this. So we will use this equation. Okay. Now let this will be as k1. So del square psi 1 upon del x square plus k1 square psi 1 is equal to 0. What is k1? This is under root 2me upon h cut, and we can write solution for this. Solution will be psi 1, now plane waves, that is a e to the power I k1x plus b e to the power minus I k1x, because this is what showing incident waves, or we may say incident beam of particles. This is what reflected waves or reflected beam of particles. So after reflection amplitude will changes, therefore amplitudes are different, a and b, and this exponential terms, here is positive x-axis, that is this incidence waves are moving towards positive x-axis, while this here minus x, that is reflected wave, will move towards negative x-axis. And also we have taken momentum p1 which tends to k1. Okay, so we have solved this, we have shown this solution. Now as we have shown solution for region first, we will see again for region second and region third also. Now using for region second, again Schrodinger wave equation for region second. So del square psi 2 upon del x square plus 2m e minus v naught, since v is equal to v naught in region second, upon h cut square psi 2 is equal to 0. This part we will take k2. So del square x2 upon del x square plus k2 square psi 2 is equal to 0. Now solution for this, psi 2x c e to the power I k2x plus d e to the power minus I k2x. So what is this? This is showing transmitted waves. Transmitted waves, or we can say this is transmitted beam of particles. Okay, this is in second region, and this is showing reflected waves, again in second region, but amplitudes are different, because in region second, when beam of particle will cross from region first to second, then obviously kinetic energy is lesser, so momentum will slow, that is momentum will vary, it means that amplitude variation will happen. So when it will reflect at x is equal to a, again there will be difference in amplitude, so C and D are taken, and here that this is moving in second region towards positive x-axis, and this is when it is reflected at x is equal to a towards negative x-axis. Okay, now we will consider for region third, writing in same manner. So again Schrodinger wave equation for region third, 2me, obviously in region third v is equal to 0, this is psi 3 is equal to 0. Now this is what? This is again P1, so writing the square psi 3 upon del x square plus k1 square, psi 3 is equal to 0, and this can be write a solution psi 3x, which is e to the power I k1x plus f to the power minus I k1x. So this is what? When waves from second region cross towards third region, so this is again transmitted waves in third region, and this is what? Reflected waves toward third region, but from third region there will be no reflection obviously, so this will be 0. It means that for third region equation will part only this, so this is of no needs, we can erase this one. Okay, so this is what we have psi 1, psi 2 and psi 3. Now to calculate R and T, we need what? We need relation between constants, and also we need for relation between constant, we will use boundary conditions, as we have used in potential step also. So now these are now solving equations terms. This will be in a continued video of this topic. Thank you.